Good morning and good afternoon, everyone. Welcome to this online lecture. I'm Kai Jiasun from Institute of Modern Physics, Fudan University, and today I will host the open seminars in Frontier of Nuclear Physics, number 44. This series of lectures is sponsored by the Department of Nuclear Science and Technology, Institute of Modern Physics, Ministry of Education Key Laboratory of Nuclear Physics, and Ion Beam Application, Fudan University, and co-supported by the Nuclear Science and Technologies and Nuclear Technology journals. The presentations will be live broadcast on the Zoom and also the co-share website platform. You may ask questions after the talk. And today we are very happy to invite Professor Stanislaw from Kochanowski University and the National Center of Nuclear Research in Poland to give us a talk in this open seminar. The talk is about the production of light nuclei at colliders, coalescence versus thermal model as the new data from STAR collaboration and ANICE collaboration. There is a very hot debate on the production mechanisms of light nuclei and hypernuclei. So Professor Stanislaw Mrowczynski is a professor at young Kochanowski University and the National Center of Nuclear Research in Poland. He received his PhD from the Institute of Theoretical Physics in Kiev in 1985. He went on to work at the GINR in Dubla and the Soltan Institute for Nuclear Studies in Warsaw and the Świętokrzyska Academy in Kiev before joining JKU in 2008. His research focuses on theoretical descriptions of relativistic heavy-ion collisions and the physics of quark-gluon plasma. He has published over 200 articles and has been recognized for his work with awards such as the Prize of the Polish Physical Society for Popularizing Physics and the prizes from the rector of JKU. And I think Professor Stanislaw is one of the earliest establishing the relation between the HBT correlation measured in heavy-ion collisions and the coalescence production of light nuclei. And so, welcome, and time is yours, Professor.
Okay, so thank you very much for the invitation and for this nice presentation. I should say that it's a real pleasure for me to give this talk. And I should tell you that I was in Shanghai. It was rather
Recording in progress.
Rather a long time ago. I was in Shanghai in 2006. There was organized Quark Matter conference. And I remember I was very much impressed with the very fast development of Chinese physics. And I can say I can observe now fruits of this development. Chinese physicists produce so many papers, they are so much active. So it is for me also a nice occasion to present my work to you. And as it was said, I'm going to talk about production of light nuclei. And now, as it was already said, there is a very hot debate. What is the mechanism of production of light nuclei? So, first of all, I would like to say that although a production of light nuclei in nuclear collisions is observed for many, many years, when we consider production of light nuclei at colliders, we have something really new. The point is that when two ultra-relativistic ions collide, in mid-rapidity, we have baryonless matter. There are no baryons coming from incoming nuclei. Therefore, we must really produce this nuclei. And also because baryon matter in this mid-rapidity domain is baryon-less, it means that we have matter-antimatter symmetry. We produce equal numbers of deuterons and anti-deuterons, tritons and anti-tritons, helium-3 and anti-helium-3, and so on. And we also produce hypernuclei and anti-hypernuclei. And there are two common approaches to the production of light nuclei. And one is coalescence model, which means that we first produce nucleons, and then due to final state interactions of the nucleons, we get nuclei. And then there is a thermal model, which assumes that at late stage of the collision, matter is in thermal equilibrium, and then all possible hadron species are in the equilibrium numbers. So the first model is a kind of microscopic model which describes how nuclei are produced. The second model exploits the assumption of thermodynamical equilibrium, and then we get the numbers of all hadron species. So, and then there is a very much impressive success of the thermal model. So here we have yields of all hadron species, and here we have the species. So we have pions, kaons, protons and antiprotons, lambdas and anti-lambdas. Here we have hyperons, and here we have deuterons and anti-deuterons, and at the end we have hypernuclei and anti-hypernuclei. And what is so impressive that in one such a very high energy collision, here we have collisions at collider, at LHC, we see we have thousands of pions, and then we have number of hypernuclei is one hypernucleus per million events. So we see that thermal model covers 9 orders of magnitude. And here we have these dots are ELIS data, and here we see predictions of a statistical model. So it is very much impressive picture. And what is very important that in such a situation, thermal model is actually very simple, because the yield of hadron species is described by a very simple formula. G here is a number of internal degrees of freedom, and then we have simply exponential function. In case of light particles like pions, except such a direct production, we have many pions which originate from decays of heavier resonances. But in case of these nuclei, which are here, the formula is really simple. So it was very surprising result. The thermal model describes these yields of hadrons so well. But why it is so surprising? Because it is hard to imagine that light nuclei can exist in a very hot fireball. And why? Interparticle spacing, so the average distance between hadrons in the fireball of temperature about 156 MeV is less than 2 Fermi. It is about 1 Fermi, 1.5 Fermi. And then we must take into account that a radius of a deuteron is about 2 Fermi. So inter-hadron spacing in a fireball is smaller than a radius of a deuteron. Then we must remember that, say, deuteron is very weakly bound particle. The binding energy is only slightly over 2 MeV, and temperature is almost 160 MeV. And then we should also take into account that the process of formation of a deuteron is a long process. So it is certainly longer than 2 Fermi over C. And why longer? Because if we have a deuteron of a radius of 2 Fermi, Then to form a deuteron, we must establish a communication between neutron and proton. So it is absolute minimum to Fermi over C. But we must take into account that the whole fireball can exist for, say, no more than 10 Fermi. So we see that the time of production of a deuteron is comparable to the lifetime of the fireball. And finally, we should remember that the fireball is essentially a classical system. And why it is important? Because when we have quantum systems, sometimes it happens that because of quantum effects, such a complicated structure can even exist in a very dense system. For example, we have such a situation with superconductors. In superconductors, we have so-called Cooper pairs. So pairs of electrons which are bound to each other. But such structures can exist because there is very peculiar quantum situation. But a hadronic fireball produced in nuclear collisions is essentially a classical system. So we cannot expect very important such an effect like those in superconductors. So collecting all these facts together, it is very, very hard to imagine that light nuclei, which are very loose, weakly bound systems, can exist in a very dense and hot fireball. For this reason, it was observed by some people that light nuclei in a fireball is something like snowflakes in hell. And there is kind of common agreement that snowflakes cannot exist in hell. And in my lecture, I will try to convince you that although it is not possible to have snowflakes in hell, we can have snowflakes from hell. So very weakly bound systems can be emitted from a very hot fireball. Okay, and now another model which describes production of light nuclei is coalescence model. But it belongs to the very broad class of physical models, which are called models which take into account final state interaction. So, and this is very conventional approach to the production of light nuclei. So let me briefly describe how the model works. So imagine we have collision of two nuclei. And then we produce many, many hadrons. But if it happens that there are two nucleons which are close in phase space, then due to attraction of these nucleons, we can have a production of a deuteron. And then what is very important in this model, that we have two very different scales. We have scale of production, of particle production, and the scale of a formation of a nuclei, of a nucleus. So for example, to produce a deuteron, we must produce a mass about 2 GeV, because each nucleon is 1 GeV, so we must produce at least 2 GeV mass. But binding energy is very small. It's about 2 MeV. So we have huge difference in this scale. And then, since the processes of high energy scale are very fast, and then of low energy are slow, we see that this big difference in energy scale can be translated into big difference in time. So production of mass is very fast process, and formation of nuclei is very slow process. And then I should say that this very old model proposed in 1960s, and in my opinion, this model has very good physical justification. And let me go to more details with this model. So when we have this very huge difference in energy scales, we can say that we can always factorize the cross-section to produce a deuteron into a cross-section which describes production of neutron-proton pair. And then we have certain prefactor which essentially describes a probability that two nucleons can form a deuteron. So this is very important, what I want to say, that because we have these two very different scales, we can write down the cross-section in such a factorized way. Okay, and now in 1980s, there was a very nice paper by two Japanese guys, by Sato and Yazaki, who realized that this process of formation of a deuteron is very similar to two-particle correlations, what in our community is called HBT correlations. And then they realized that this factor, which is here, which describes probability to form a deuteron having two nucleons, can have very simple structure. So this functions d is a simply distribution of emission points of, say, proton. And the second one is a distribution of emission points of neutron. And then we project this on a deuteron wave function. Additionally, what is important here, we have spin factor, because when we have, as you know, deuteron has spin 1, but two nucleons can exist in four states. There are four possible orientations of spins. So, and particle with spin 1 has 3 states. So this 3½ simply reflects the numbers of states. Okay, and now let me say a few more words. So here we have this wave function of a deuteron is a two-particle wave function because it describes neutron and proton. But as you know very well from elementary physics, we can always separate center of mass motion from the relative motion. So if we remember that the function, two-particle wave function, can be always described in such a way that this is a wave function of relative motion and plane wave of a motion of center of mass system, where these new variables are defined in such a way, this is relative distance, and this is position of center of mass, we can get simpler formula where we have not integrations over two positions, but only one. And here, this quantity describes not a position of emission points, but this is distribution of relative distance of neutron and proton at the moment of emission. So, but there is one also very common misconception, because this formula looks like as neutron and proton would be emitted at the same time as they were emitted simultaneously. However, this formula actually can include this difference in emission time. This formula can be obtained a bit differently. We include time, that we include the effect of time, the time difference in emissions, but at the end we get exactly the same formula, but the radius of the source should be understood as a genuine radius plus duration of time which is used to emit particles, or you can say differently, tau. So Rs is a radius of the source, and tau is lifetime, and V is a velocity of a particle which is emitted from the source. So once again, this formula does not include time. However, when we parameterize this function, this radius should be understood as an effective radius, which takes into account both spatial size of this source, but also its lifetime. Okay, and now I would like to, so this is this formula which was discovered by Sato and Yazaki, but then it should be compared with very similar formula which describes two-particle correlation. So imagine we have two very similar objects. One is deuteron, and another one is neutron-proton correlated pair. And actually, at low energies, people measured neutron-proton correlation function. And then what is very important to realize that these two formulas are very similar to each other. We have exactly the same function which describes of emission points. And the difference is in the wave function. This is the wave function of bound state, and this is the wave function of neutron and proton in a scattering state. So therefore, this function depends on the relative momentum of neutron and proton. So the correlation function is a function of relative momentum of neutron and proton. And all these problems are discussed in all details in my old paper, which is mentioned here. Okay, and what is the meaning of this coalescence formula? So now let me explain what is the physics behind here. So imagine we have here time, and now imagine that we have particles which are in a trap. So they are kept in a container. They are kept in a container, and as long they are kept in a container, we have a wave function psi. Suddenly, we open the container, and particles start to fly away. So TF, it is what in our field is called freeze-out time. It is this moment when we open the trap, and then particles start to fly away. So as long as particles were in the container, so we have one wave function, and once we open the container, we have another wave function. So if we are interested in transition matrix element, then according to the quantum mechanics, how we should proceed? We should take the wave function here and project it on wave function of interest of the state we observe after the particles are escaped from the trap. So, and then we take such a projection, and then we take the square. And now we should observe that we can write down this square as a double integral. So we have now this function, so we have integral over r and r prime, and we have also these wave functions which are shown here twice. And now very important point. When we have many particles, we should not use wave function, but we should describe it by means of so-called density matrix, because we have not pure quantum state, but we have rather open state. For this reason, we should describe the system in a trap using density matrix. And then we have density matrix here, and then we have this state of a system after the trap was open. And now you see that now I can describe this in such a way. So if I replace this object by density matrix. And now very important point. In statistical physics, we use something what is known as random phase approximation. So because of this random phase approximation in quantum statistical, even so we consider quantum statistical mechanics, we still deal with probabilities, not amplitudes. And then here we have quantum amplitudes. But if we assume that density matrix is diagonal, then we have only probabilities. So this random, so the assumption that density matrix is diagonal is equivalent to the well-known approximation, which is called random phase approximation. And then we get this formula, which should be compared with either this one or that one. So once again, so I should say that this formula has a very good theoretical justification. It describes such a situation that till a certain moment, our particles are kept in a container, and suddenly the container is opened. And then in our field, in case of nuclear collisions at very high energy, we have particles in fireball, and then we have so-called freeze-out time. The system is big enough, the mean free path start to be comparable to the size of the system, and then the whole system decays. And this is this freeze-out time. So in my opinion, this formula has very, very good justification, has very good foundations. Okay, there is one very common misconception that it started with the very early paper by Butler and Pearson. And then there is kind of a simple observation. If we have two nucleons, here nucleon and here nucleon, and if they are on mass shell, so if energy square minus momentum square equals mass, so if this nucleon and this nucleon is on a mass shell, then it is kinematically not allowed to have a deuteron, because then we are unable to satisfy energy and momentum. But in my opinion, and I'm deeply convinced that this is simply wrong, incorrect reasoning. And why it is incorrect? And then there are two types of arguments. One refers to the theory of scattering. So if we have problem of scattering, we have initial states and final states. And then initial states must be on mass shell, and the same holds for the final state. But theory of scattering doesn't require to put on mass shell particles which are in intermediate state. These particles are described by propagators, and there is no requirement to put these particles on mass shell. So this is kind of a formal argument. But there is also physical argument. Imagine that you have a fireball of the radius Rs. Then Heisenberg uncertainty principle tells us that we cannot determine momentum of particle emitted from some such a source with higher accuracy than 1 over radius. So we know that the momentum cannot be determined precisely. And now what is very important, size of a fireball is comparable to the size of a deuteron, and is comparable to the inverse binding energy of a deuteron. Therefore, this certain uncertainty in momentum is completely sufficient to produce a deuteron. So there is no problem to satisfy momentum conservation and energy conservation. And so because of this problem with energy and momentum, when we have particles are on shell, it was very often stated that we need a third body to allow for this process. In my opinion, it is completely wrong. The point is that these are intermediate particles which are not on mass shell. And I must say that I am rather proud of this observation, because which I made many, many years ago in this very old paper from 1987. So in my opinion, there is no problem with energy momentum conservation. Okay, and now what is the situation? You have two models, thermal model and coalescence model. And the problem is how we should decide which model is right and which model is wrong. And we see that this, and then the observation is that these two models usually give quantitatively rather similar predictions. So, following the terminology of great philosopher of science, of Karl Popper, one can ask how to falsify one of the model experimentally. So we should find such a measurable signature that could tell us which model is right and which model is wrong. And here I move to something what I did more recently. So the first idea is the following. So I strongly encourage experimentalists to measure hadron-deuteron correlations. And then, and why? Because I will try to show you that when we measure hadron-deuteron or deuteron-deuteron correlation, then we are able to decide what is a source of a deuteron. And what is the question? Whether we have such a situation that we have a source, and then we have a hadron emitted and a deuteron emitted. And then because of the final state interaction, we have certain correlation between hadron and a deuteron. But we can have two situations. In one situation, hadron and deuterons are emitted directly from a fireball. And in the second case, we have hadron emitted, but neutron and proton. And then at the same time, when there is correlation created, we have also the process of formation of a deuteron. And the point is that this process of a formation of a deuteron and creation of a correlation is of the same time scale. And okay, and let me now explain this in more detail. So let me first assume that deuteron is elementary particle. So if it is treated as elementary particle, we have a source and we emit hadron and deuteron. And then we ask, what is the correlation function? So we should measure distribution of deuterons, distribution of hadrons, single particle distributions, and compare it to the distribution of pairs when we register at the same time hadron and deuteron. And then when we construct such a quantity, the multiplier here is correlation function. And then, as I already said, and it is a long story, there was a very beautiful, very old paper by Steve Koonin and Richard Lednicki and Vladimir Luboszyc, who explained us how to compute the correlation function. So this I already had, that we have distribution of emission points of hadron, emission points of deuterons, and we have wave function of hadron and a deuteron. And we should compute such a overlap integral. And then how we proceed? So we again must separate center of mass motion from the relative motion. So we have plane wave of center of mass. We have wave function of relative motion with the relative momentum q. So we introduce this relative variable and center of mass variable, and we get the well-known formula. And this distribution with the index r is constructed in such a way that this is, here we have single particle distributions, which were here, single particle distribution of hadron and of deuteron. But since we managed to describe in this way, so we must take the integral and we get this formula. And then this, if we assume that this single particle distributions are Gaussian, then this distribution of relative distance is also Gaussian. And we observe there is also different factor here. Here we have factor of 2, and here we have factor of 4. Okay, and now we have different situation. Now we treat deuteron as a bound state of a neutron and proton. So now the situation is different. So how to construct experimental distribution function of hadron and deuteron? since neutron and proton are emitted from the source, so here we have single particle distribution of hadron, of neutron, and of proton. So we have 3 particles. And at the end, we have correlated pair of hadron and deuteron. But here we have 2 factors. First, neutron and proton must form a deuteron. So this is described by this object, which I already discussed. This is which appears here when we have pair of neutron and proton and we form a deuteron. So this describes formation of a deuteron. So it is this factor. And this factor describes correlation function of hadron and deuteron. And now, let me move here. Here I had this correlation function when I had only 2 bodies. Here I have very analogous formula, but I have 3 bodies because I have hadron, neutron, and proton. Now I have also three source functions. The distribution of positions at the moment of emission of hadron, neutron, and proton. And here I have distribution function of these 3 particles. Okay, and now what is important, what is here, I compute as I did it previously when I simply computed deuterons. So this is known how to compute. And what remains, so I have to compute this 3 particle integral. So now this separation of center of mass and relative motion is more complicated because I have 3 particles. So I have a position, center of mass of 3 particles, a relative distance between neutron and proton, and here I have relative distance between hadron and center of mass of neutron and proton. This is actually called Jacobi variables. So I write down my function in such a way, and then I get distribution, I get this correlation function. And then if I use Gaussian parameterization of the source, I get the function, which is correlation function of very form, which strongly reminds us what I got previously. However, there is one difference. So if I consider such a situation that I treat deuteron as an elementary particle, I get this formula. If I treat deuteron as such a bound states of a neutron and proton, I get this formula. And what is the difference? The difference is that I have different source function. Here is factor 4, here is factor 3. So measuring precisely correlation function, I can distinguish this from that. But the numerical factor is not very big. Okay, so here then I wanted to see whether whether this is observable difference. So I have to compute correlation function. So I follow the method introduced by Lednicki and Luboszyc. We write down the wave function in so-called asymptotic scattering state. We use so-called only S-wave amplitude. So here is scattering amplitude. And then if we have S-wave scattering, then it has a very simple form. And there is only one parameter, which is scattering length. Then we must also remember about Coulomb interaction. So the simplest way to take Coulomb interaction into account is to use so-called Gamow factor. So if I combine this all together, I can get proton-deuteron correlation. But here there are some technical complications because when I have proton and deuteron, then I have pair of such a proton-deuteron can exist in a spin 1/2 and in a spin 3/2. So I must compute correlation function in these 2 states, and then I must average to take average value. thanks God, there are the scattering lengths in this channel of spin 1/2 and 3/2 are known. And then I here give examples of this correlation function of proton and deuteron, and for the sources which are equal to 1.73, 1.5. And I took these numbers in such a way that they differ by this factor square root of 4/3. It is this factor which appeared here. Okay, and now, so we see that these correlation functions significantly differ from each other. So if experimentalists are able to measure the correlation function with such accuracy that they are able to distinguish this curve from the neighboring curve, then they are able to say what is the source of a deuteron, whether we have such a situation or such a situation. Okay, and now one more step can be done, because numerically the effect is bigger if we consider not proton-deuteron, but deuteron-deuteron correlation function. Because then what is the situation? In one situation, we have two deuterons simply interacting with each other in final state, and we have correlation. In the second picture, we have 4 nucleons emitted from a source, and then we have situation analogous as in here, because we have, so in one picture, we have 2 simply deuterons treated as elementary particle, and this is the situation like in thermal model. 2 deuterons are emitted from a source and they are correlated. In the coalescence model, we have pairs of nucleons emitted. So at the same time, when this correlation is created, we have also formation of deuterons. And here we have again the same form of the correlation function, but numerical factor in source function is different. Okay, and we computed with my student correlation function, and we see that there are sizable differences. Okay, and so what is my suggestion? My suggestion is to measure proton-proton, proton-deuteron, and deuteron-deuteron correlation function at the same time, in the same conditions, and then I believe that we will be able to say whether the source function of deuterons is like this or like this. If we see that it is this case, then we can conclude that formed deuterons are emitted from a fireball. If we see source function like this, then we say no, nucleons are emitted from a fireball and deuterons are formed later on. Okay, so it was the first idea, and now let me briefly sketch only the second idea. The second idea is related. What is the idea? Imagine we have 2 nuclides. One is helium-3 and one is helium-4 and lithium-4. And what is the difference? That this is very well bound alpha particle, which is very compact with very high energy density. With very high binding energy. And lithium-4 is such an unstable nucleus, which after a very short time decays into helium-3 and proton. So it has such a structure. What is also important, this has spin 0, this has spin 2. Then what is very important, the mass is very similar, because this is at the scale this is almost 4 GeV. And then there is difference in binding energy, but this binding energy is not very different. And then we can argue in the following way. If we have thermal model, then simply the number of this lithium nuclei should be 5 times more than those, because the mass is more or less the same, but we have 5 spin states. So we have very specific prediction in case of thermal model. But in case of coalescence model, then it is much more complex because it depends what is the structure of this nucleus. And what I did with my other PhD student, we computed this ratio and how it goes. So we must compute probability to produce a 4-nucleon system. So we have 4-nucleon wave function. We have 4 source functions. But what is the difference? The difference is that in case of a helium-4, we have very simple wave function. It can be constructed using such a Gaussian parametrization where R1, 2 is a relative distance between nucleon number 1 and nucleon number 2, and so on. But in this case, in case of lithium, the structure is much more complicated. Here we have something like helium-3, but then we have one proton orbiting this helium-3. And then it is known in nuclear physics how such a wave function can be obtained. So we have this part of wave function, which describes this part. And then we have orbiting proton, which is described here. And here we have this spherical harmonics, which describe this motion of a proton. And then probability to observe helium-4 or lithium-4 is essentially encoded in the difference of wave function. So what is the point here? That thermal model is independent of wave function, while coalescence model strongly depends what is the wave function. And here there was some technical work. So here we just have chosen simple Gaussian parametrization of the source function. Then there are certain problems how to write down the wave function. One can use so-called Jacobi variables, which greatly simplifies a computation. I will not go into details, but what is important that using these Jacobi variables, we can perform fully analytic calculations. Okay, and then what is the outcome? The outcome is that we can find these probabilities for a formation of helium-4 and lithium-4. Here there was a problem how to precisely construct this, because we know that lithium-4 has spin 2, but then the question is how we can have orbital angular momentum, but also spin. And then at first glance, it seems that we can have 2 possibilities, that orbital momentum is 1, and then we have spin 1 gives, and then they sum up to the spin 2 of the whole system. But when we did this paper, I was not aware of this, that also parity of the state is known. And now I know that only orbital momentum L equal 2 is the right. And then we have certain parameters, root mean square of the source, root mean square of helium-4, root mean square radius of lithium-4, and then root mean square radius of this cluster helium-3 in case of lithium. So this which is here. Okay, and now collecting all this, so as I told you, when I take this ratio of yields, in thermal model it is simply number 5. And how it looks like in case of this coalescence model. So here we have lithium, here we have helium, and here we have ratio. Unfortunately, we don't know what is the radius of this nucleus. So here are computation for different radii, and then here I have as a function of source radius. And now what is very important? When we perform experiment, we can choose collision centrality. And when we have peripheral collisions, we have for sources which are smaller, and in central collisions, we have higher. And then what is prediction of this paper? So we predict that in coalescence model, this ratio of lithium to helium-4 should be centrality dependent. In case of thermal model, it should be simply flat and equal about 5. Actually, when we take binding energies into account, it is less than 5. But what is important, it is fully flat. And in coalescence model, we should have a strong dependence. And what is important, then I looked into old literature, and then it appears that lithium-4 was observed both at rather low energies and also at AGS. So I think that is experimentally possible. Here is certain technical problem because lithium-4 is unstable nucleus which decays. So there is a problem how to compute number of these nuclei which are observed in the final state. So here is certain technical problem that we should measure proton-helium-3 correlation function, and from this correlation function we should extract the number of lithium-4. But this is rather technical issue, so I am not going to discuss. So we here in our paper we precisely explain how number of this lithium nuclei should be computed. And now let me go to the conclusions. So my conclusions are the following. So I discussed two ideas to how to distinguish thermal model from coalescence model. So the first observation is that hadron-deuteron and deuteron-deuteron correlations carry information about source of deuterons. And then if we measure, and now we suggest to systematically measure proton-proton, proton-deuteron, and deuteron-deuteron correlation functions, and then we could decide what is the source of deuterons, whether from a source there are nucleons emitted or deuterons. So I believe that measurements of these two functions that these functions are sensitive enough to the size of particle source. And I think that we could get an information directly which model is right. The second idea was to perform measurements of two nuclides, of helium-4 and lithium-4, and to compare how this yields change, in particular with centrality, because when we change centrality of collisions, we also change radius of a source. For this reason, I believe it is then also possible to distinguish thermal model from coalescence model. And that is everything. Thank you very much.
Okay, thank you very much, Professor Mrowczynski, and has given us a very comprehensive introduction to the thermal and coalescence production of light nuclei, and especially he proposed two good observables which is accessible to experiments, and which would be hopefully could be measured in experiments and used to distinguish between the two production mechanisms of light nuclei. And now it's open to questions in the audience. If you have any questions, just talk through Zoom. Let's see. If perhaps maybe I have one question. So as for the lithium-4, I think as you know, the hypertriton also has a very large radius as compared to helium-3 and deuteron. So it is also, I think it is also a good observer to allow us to distinguish distinguish the coalescence and thermal model.
Yeah, I absolutely agree that this idea I presented is very similar. What was done by the group by Chemin Ko, who computed also production of hypernuclei. But what is one advantage of lithium is that when you have hypernucleus, so hypernucleus you could compare with helium-3 or triton. But then, because you have lambda, then the mass is not the same. And what is nice here, that we can, when we have helium-4, we have helium-4 and lithium-4. The mass is almost the same, and for this reason, we have the simple situation that in case of thermal model, we have the ratio should be flat as a function of centrality, but in case of coalescence, we should have strong dependence. And we don't have this simple signature in case of hypernucleus, because if you take the ratio, say hypernucleus to triton, then you will presumably have certain dependence on centrality, because production of lambdas will be different than production of nucleons. So for this reason, I think that this lithium is interesting. But I agree that this is rather a quantitative issue, that we can also do something similar with hypernuclei.
Yes. Okay, thank you. So now ENA has a question.
Hey, hello, can you hear me?
Yeah.
Thank you, Professor Stanislaw. I enjoyed the talk very much. So I have a question related to the calculation of the proton-deuteron correlation function. So in your calculation, I see that for the outgoing channel, you only have two particles, the proton and deuteron. But I wonder, because for the ion-ion collision, there will be also I think, other particles. For instance, helium-3, you mentioned later for lithium-4 case. But if there's also some final state interaction between, for instance, helium-3 with this proton, then how this interaction will affect this proton and deuteron correlation function?
Okay, I think that the situation is the following, that of course, when we have, or maybe I will go here. Oh, here. So you are right that when we have nucleus collision, we produce many particles. And then one can ask, well, why this nucleons interact? And what about interaction of nucleons with this hadron? Or with this hadron? But what is very important here, that the final state interaction plays only important role when we have particles which are very close to each other in phase space. What does it mean? That they must have very similar velocities, because when they have the same velocity, then they travel for a very long time in the same direction. So they are for a very long time in contact with each other. But so, and then even so, if we even produce many particles all around, this particle is in contact with this nucleon only at the beginning. As long as they have different momenta, after some time they will be separated very well. So in my opinion, there is not a serious problem of interaction of, say, of these nucleons with other hadrons, because only the interaction occurs if particles have very close velocities, because then they travel together for a long time. And what is important, this final state interactions are interactions of very small energy scale. So these are very slow processes. So to produce a sizable effect, particles must travel for a very long time together. And this happens only if they have very similar velocities. So it is my answer and my understanding.
I see. Thank you.
Okay. Professor Chunwang.
Yeah, very, very interesting talk. So I have learned a lot. My question is that, you know, all the nuclei, the wave function you can calculate from from the share model or from the nuclear structure model very precisely. Can you use that wave function to calculate the yield?
Yes, I think that. So, for example,
but from your calculation, you only assume that the wave function like a very this kind of a wave function. This function is similar to the Gaussian form. I mean, it's very close to the Gaussian form. So yeah, I mean, yeah, all these nuclear structure model can give you the very precise wave function. Then maybe you can use this to calculate, to do the calculation.
I absolutely agree that.
Yeah, so
I absolutely agree that it would be very nice to have precise knowledge. And I should say that I know that Laura Fabietti, who I guess you know her, she's very much involved in this type of measurements. So I know that she attracted to this community some low energy nuclear physicists just to provide. She was very much interested in this proton-deuteron correlation. And they made a lot of effort to have the correlation function of such as 3 nucleons to describe it very precisely. So I fully agree that now nuclear physics provide us very good methods to precisely calculate the correlation functions, the wave functions, sorry. So I fully agree that it is very important to have realistically. In my calculations, I only wanted to show how all it works, but there is a lot of space for improvement, and we should certainly use knowledge from nuclear physics how to precisely compute wave functions. Absolutely.
Yeah, I mean, this method is very, very good. I think it's reasonable and very beautiful. So I think if you could use the wave function calculated from some nuclear structure model, that would be perfect.
Yeah, I fully agree.
Thank you.
Yeah.
Jie Zhao.
Yeah. Thanks for your very nice talk. So, I just curiosity is there any experimental data on the like proton-deuteron correlation function, or just say why there is some difficulty for this kind of measurement?
No, I think that there are. I guess that in the audience there are some members of ALICE collaboration.
Yeah, actually, we've done that. We've done that in, but it's not released yet in lead collision. And for PP collision, you can find, as you just mentioned, Laura, her group did the full measurement. I think Alice had already released it last year. Actually, we invited Laura last year as one of our speaker in this in the very same seminar. So yeah, you can take a look about that. For STAR, I'm not sure, but I see some STAR members also joining this.
I know that there are.
Maybe you can. Yeah. But I mean, in ALICE, for PP, it's officially released, so you can take a look. And for lead, we've done the measurements together with the Warsaw group, but it's still a bit private yet. Okay.
Yeah. I know that there are however, what is the problem with here? I would like to have correlation functions at rather small sources. So rather in case of lead, this should be rather peripheral collisions. The problem is that if we have big source, the correlation function is very much dominated by Coulomb repulsion, and we can't see the structure. So the correlation function looks more or less like this. It goes simply down. But I should also say, and that my computation is rather schematic. What is the main problem with my calculation? It is I treated in a very simple way Coulomb interaction. And the problem is that we should have precisely treated Coulomb interaction. And the problem is that we have interference between Coulomb and strong scattering. And I must say that my computation is very schematic. I simply wanted to get an idea whether we have sensitivity, which is experimentally, but my computation of this correlation function is far not precise. So I am fully aware, and I am very glad that Laura Fabietti in particular attracted some people to perform much more realistic calculations. So my calculations, what concerns quantitatively, are not precise. I am fully aware of this.
Yeah, I think in our group there are some students have experience in calculating the HBT correlation. So maybe we could ask some students to carry out similar calculations, but based on like MPT model or hydrodynamics model, which provides a more realistic kinetic result in hypersurfaces. So. Yeah, I remember you made a one comment about the introducing the third particle to conserve the energy. Right. I think your argument is you have give a very good strong argument. But I think there is another issue. So in the coalescence model, when for instance in the when you evaluating the deuteron production, right? You consider deuteron is made of comes from the coalescence of a neutron and a proton, right? Do you also consider like deuteron made from 2 neutrons and 2 protons? Because in the kinetic approach, one can consider the 2 protons form a deuteron by emitting a pion to conserve the isospin. But it seems that there is no such processes in the coalescence calculation, right?
Yeah, but I think that. But I in my opinion, this is when. Let me go to this picture, because what is very important that when we have here, I consider such a coalescence and there is no pion production. I agree that in principle, when we have here, say, two protons, we of course must change the charge and isospin so we can emit pi plus. So
yeah,
principally it would be possible, but then it is no long. But please take into account that when we emit pi plus, so it is we must produce mass of 140 MeV plus certain momentum. So it is rather different situation than when we have formation of a deuteron from neutron and proton, because everything what the energy scale is binding energy, which is 3 MeV. In case when we produce a pion, it is 140 MeV. So it is process at significantly bigger scale. So this process must be much faster. So this is. And here, what in my opinion is very important, that we should have a nice scale separation. So production of particles and formation of a bound state. And then I would say, for me, these processes must occur earlier. So I would say okay, you are right. Before this, we have this neutron and proton pair. One proton, for example, had to get rid of some energy and emitted a pion. But all these processes are here. And this slow process, which leads to the formation of deuteron, originates much later. And here you have neutron and proton. But at earlier stage, we have such a processes as you described, that we have hadron-hadron interactions. So it is certain idealization what I discuss. But okay.
Yeah. So is it? I mean, is it possible there are some deuterons from the coalescence of like you described at a very late stage, takes a long time. And there are also some deuterons that somehow survives the expansion of the fireball, and so I mean not through coalescence. Some of the deuterons are formed not through the coalescence, but from some reactions like 3-2 or 4-2.
Okay, so
process.
Of course, okay, I agree that here I have such a nice separation of scale, but I agree that when the system evolves and this hadron gas is very dilute, then of course we can have deuterons produced before freeze out. And
yeah,
there is not such a clear cut. I consider such an idealistic situation that I say I have fast processes and slow process. But this process you described with 3 particles which have very similar momenta, this is intermediate step. And of course it can happen. I cannot object. But
okay.
Yeah, but then the treatment here I have nice. So here everything is built on this scale separation, and then I have this simple factorization that I say here I have production of pairs, and here I have only formation. If we don't have this big scale separation, we can't use this formula because it assumes that what is described by this is a very small energy scale, and here is large energy scale. And then we have, otherwise we should have kind of integral and not simply such a multiplication. So the model gets much more complicated, in my opinion.
Yeah, I think the formation of light nuclei and hypernuclei is essentially a quantum phenomenon. So you have made good predictions, I think, which will be testified in the near future, I think.
In this form, the model is very simple. If we introduce such an intermediate part, then we don't have the separation. Model becomes very complex.
Yeah, I agree. Yeah. So any more question? Let me see. Okay, all right. If there is no question, I think we already have 1 hour and 15 minutes. I think we have learned at least I have learned many more things in your talk, and we hope we can, if you have planned to visit our institute, I would be we would be very pleased.
Okay,
right.
so okay, thank you very much. It was my pleasure to give this talk, and I am very glad that I attracted some interest. And I hope there will be another occasions in future for discussions. So thank you again very much. It was a pleasure.
Yeah, thank you very much. Okay, thank you very much. All right, then I will close this meeting.